Good evening and welcome to what is really the last evening seminar of 8.224, Exploring Black Holes for this academic year. I'm Professor Ed Bertschinger, and I'm going to be talking about cosmic structure formation, from cosmic inflation in the early universe to the formation of galaxies. Let me put up a slide showing in pictorial form outline what this talk is going to be about. It is really the sequence of the universe starting from the dawn of time, a tiny fraction of a second, to a state of tremendous fluctuations and inflationary expansion, through to the era when we see the cosmic microwave background radiation, and finally to our present-day universe filled with galaxies, with planets, and teeming with life. Now, this is a kind of a schematic in concept showing some of the key moments and qualitative features of the universe over this 13.7 billion years. On the side board, I've been a little more quantitative by listing times of certain events in the universe, the thermal energy of particles, Boltzmann's constant times temperature, that's an energy per particle, and then the event that is characterized by that time. Cosmologists like to describe events in the universe less by their time than by their temperature. And the reason for that is time and temperature have an inverse relationship. The universe is expanding. An expanding gas cools by adiabatic expansion, just like if you let the air out of a bicycle tire, it feels cool. Conversely, if you compress it, it gets hot. And we know that if the universe started in a very hot, dense phase, then it went through this sequence of temperatures. We're very confident about that. We have direct evidence that the universe at early times was at least as hot as 10 kilo electron volts. That is about 10 to the 8th degrees Kelvin, 100 million degrees Kelvin. What's the evidence we have for that? It's the helium in the universe. We know, therefore, that the universe started in a hot, dense state. We know that today its temperature is 2.7 degrees Kelvin, much colder. So it went through this sequence of temperatures and therefore through the sequence of physical events characterized by those temperatures. What we know less well is the time at which each of those events occurred. And it is only in the last couple of months that, for example, we've learned that the age of the universe today, 13.7 gigayears, we know that to about 1% accuracy. If you'd asked me that question at the beginning of the semester, I would have said it's about 14, give or take 1 or 2. So now we know that number fairly well, and I could make these other numbers a little more accurate, but what really counts is the temperature. So as we look in this kind of storyline for the universe, the events that we're trying to put together in our picture of understanding the universe start from high energies, early times with the inflationary era Professor Alan Guth talked about in his talk. And then as we go to lower and lower temperatures, we probe physics that's a little bit simpler than the physics of inflation. Actually, inflation itself is a very simple phenomenon, but the particle physics that inflation is based upon is particle physics that we still don't understand since we haven't probed it directly in terrestrial laboratories. Much of the excitement about the study of the universe is the hope that we can learn something about particle physics at these tremendous energies by looking at the relics, the remnants of this early phase left over in our universe. So I'm going to be highlighting the role of inflation. I'll be highlighting the role of the microwave background. Shortly before the microwave background radiation was released to us in the event that we call CMB decoupling, there was a change in the universe from a radiation-dominated phase to a matter-dominated phase. We call the current era the matter era. Actually, if this were a little more precise, I'd say that just before today, just before this now, the universe has become dark energy dominated. But I didn't put that down on this diagram since the dark energy seems to have very little to do with anything else in cosmology. It's a big puzzle, and it has little effect, very little effect on galaxy formation, for example. But we'll focus on inflation as a source of fluctuations in the early universe, the microwave background as a signpost of those fluctuations, and then the physics of gravity amplifying those fluctuations to form galaxies starting about 1 billion years after the Big Bang. So I've already alluded to the fossil relics that we use to study the early universe. They are the cosmic microwave background radiation, galaxies themselves, and indeed all the matter in the universe, atoms, dark matter, and dark energy. These were, we think, produced in the early universe. And if we understand well enough what these substances are, how they interact, how they were produced, then we have some information about the particle physics of the early universe. And that is one of the great excitements of the subject to physicists today. Now, so much has been learned about the microwave background from the recent results of the Wilkinson Microwave Anisotropy Probe satellite that I'd like to spend a moment talking about it. You heard from Professor Lyman Page of Princeton about the first results from this satellite mission. They're really spectacular. They have really taught us a lot about the early universe. And I will show you an animation of this, describing a bit about this satellite mission, just to show what it is that we see when we look at the microwave background radiation. First of all, this is an artist's conception of a galaxy, perhaps like the Milky Way galaxy, with some companions, satellite companions. And we're going to take an imaginary space flight here, flying through our galaxy, imagining that we lay in the disk of stars and we see this beautiful star field, the Milky Way galaxy. In fact, this is perhaps even an optical photograph of the Milky Way. Now, imagine our space flight has taken us to the Earth, and we put a grid on the sky. And we've just moved superluminally outside of our universe so that we can see it on a sphere from the outside. Unfold that sphere onto a sheet of paper, and that's what you have. Now, let's look at the appearance of our galaxy in the sky in different wavelengths, from the optical, the infrared, submillimeter, and millimeter waves, going from high energy photons of the optical light to low energy photons of the microwave background. And this animation is really cool because it shows at one time both the different kinds of emission that exist in the universe, and on the other hand, it brings out the physics a little bit of the fluctuations in the microwave background. I'm going to replay it for you, but before I do, let's look at this image, the final one. This is a map of the sky in the microwaves with the contrast turned up. And if you watch it again, you'll see that before that contrast knob was turned up, you know, television sets used to have a dial that you could turn called contrast. Now I think everything is by computer and digital. But sharpening the contrast means you change the scale of black and white or of colors to bring out features that are otherwise hidden in the dim, uniform intensity. And that was really clear in this microwave map before the contrast bar was moved up. This was almost a uniform gray. And that's because the cosmic microwave background radiation is such a strong light source at the microwave wavelengths, it almost makes a uniform brightness around the sky. Now what's left over is this red band. That is the band of our Milky Way galaxy. The same residual that we see with stars in the visible light, with gas clouds at other wavelengths, the infrared, and so on. That shows up in the microwave as well. So this is from our own galaxy. It's what we call a foreground for the cosmic background radiation, the stuff in the blues and greens. And what the blues and greens show are the fluctuations produced in the early universe during inflation, which then subsequently amplified to form galaxies. Now, I really love this animation, so I want to show it to you again. The model of the galaxy here is a little bit hokey. You can see how the stars kind of just turn on when you get close to the disk, and then they fade to this beautiful star field. But what I love is the way that the celestial sphere, we think of a sphere surrounding us, and just like you can take a sphere, a globe of the Earth, and project it onto a flat screen, so you can do with the sphere, celestial sphere around us. And here is the Milky Way galaxy in the optical light, It's really gorgeous. Not so gorgeous in that view. The infrared, there's this band that you see for a short while in the infrared. That's actually the plane of the solar system, the ecliptic plane with dust. And then this nearly uniform brightness that only reveals the fluctuations once you turn the contrast way up. Those are the tiniest fluctuations, a few parts in 100,000 left over from the early universe. And they were measured by this satellite, the Wilkinson Microwave Anisotropy Probe. Now, what did the satellite do for us? Well, once you subtract away the galaxy, which is possible by combining slightly different color images, the galaxy has a different spectrum, you can make a map of the microwave background. This was the map made from data taken 10 years ago by the Cosmic Background Explorer satellite. It was the mission that first found these fluctuations and gave us confidence that the inflationary model and our ideas about cosmology were on the right track. Well, now I'll show you how this picture gets refined by WMAP, and you'll see not only were we on the right track, but we begin to see the exquisite detail that modern technology can show us. And there it is. We can go back and forth between these two maps, and it's like being nearsighted and then finding your glasses, putting in your contact lenses if you're me. You get to see a whole lot more structure. And that means we can see more of the inflationary fluctuations and therefore learn more about the universe now in 2003. Well, what are those fluctuations? We say they're inflationary fluctuations, but in fact what they are is sound waves. Sound waves traveling through the ionized gas, the plasma in the early universe. Those sound waves started from the Bang, the Big Bang, with the cosmic inflationary era that set the expanding universe into very rapid motion. And there are really two main outcomes of inflation. One is that produces a very large universe, spatially close to flat, a large old universe with very small spatial curvature. That's been confirmed now by the microwave background measurements. But it also imprints very small fluctuations of energy density or of temperature on this gas. And if you have small fluctuations of the density or temperature of a plasma, an ionized gas, you have sound waves. And I'm going to play for you a synthetic sound file of what these fluctuations, inflationary fluctuations, would have sounded like about 1 second after the Big Bang, so about the time of neutrino decoupling while helium was being produced in this fiery furnace of the Big Bang. I'm going to play that. That's how it would have sounded if you were there. Almost how it would sound, as you'll see. I'll explain. It sounds like you turned on your television set and there was no channel. Well, that static is really how it would have sounded because the quantum fluctuations are random. They're random noise. And the static that you have on a television set that's not tuned properly or a radio set that's not tuned to a station is just noise. Now, there's one thing about that noise signal I played that's not true to the actual sound. The pitch, if you listen carefully, this pitch isn't changing with time. But the actual sound waves produced in the universe would redshift, and the pitch would change with time as the universe expands. So this first sound file is actually not correct. That's how the sounds would be if your frequency standard were changing with the expansion of the universe. But if you were there with your ear hearing the sounds, about a second after the Big Bang, it would sound like this. And that whistle, that lowering in pitch, is exactly what you expect for the Doppler shift of something moving away or for the cosmological redshift. the frequencies decrease inversely with the expansion of the universe. And the universe expands by a factor of 3 or so during the time of that sound file, 1 second after the Big Bang till about 4 seconds after. I guess it expands by a factor of 2. So that's what those fluctuations would have sounded like. And when we look at the microwave background radiation, we see a snapshot, frozen in time, a frozen moment of those sound waves, 380,000 years at this moment, microwave background decoupling, after the Big Bang. Now I'm going to show you a series of 3 images which go from what the WMAP satellite actually observed, which is not the pretty blue and green pictures I showed, but actually more like this. And I'll show you how they arrive at that high contrast, beautiful image of the inflationary fluctuations. First of all, the WMAP satellite looked at 5 different frequencies in the microwave. It's like having a radio receiver that actually could measure 5 different radio stations at once. And the reason it did that is that there's a certain dependence on frequency predicted by fluctuations from the Big Bang. They should have this black body spectrum, whereas other sources of radiation would deviate from this black body. So for this first image, what the WMAP team did is just to use 3 of the frequency channels, and it color-coded them in false colors. It made 1 red, 1 green, and 1 blue. And you know that if you take an equal weight of red, green, and blue, you get white, or gray, or black, depending on how much red, green, and blue you take. So radiation that has the black body spectrum is gray, or white, on a grayscale in this image. Radiation that departs from the thermal spectrum is a different color. And here you can see impressively clearly radiation from the Milky Way galaxy in these red spots, because the emitting gas clouds in the Milky Way galaxy are not at 2.7 degrees Kelvin. Now, one other thing you see in this map is what's called a dipole pattern, the fact that this upper right-hand portion of the picture has brighter intensity than the bottom left-hand. Now, one interpretation is simply that the universe is hotter in this direction by a few thousandths of a degree Kelvin. Another interpretation that is equally acceptable and more likely physically is that the universe has no such dipole pattern, but we are moving relative to this radiation. The photons flying through the universe are like a swarm of bees, and the swarm of bees can be coming towards you, or moving away from you, or sitting right on top of you. And it so happens that it is coming towards us in this direction because the Milky Way galaxy, the sun orbiting around the galaxy, are moving. Well, we know how to correct for the Doppler shift, so we can go to the cosmic rest frame, removing that dipole, and this is the pattern we get. Not only have we removed the dipole, we've also increased the contrast so that the smaller fluctuations are brought out in intensity, and the Milky Way galaxy is even more prominent now. In fact, not just the Milky Way galaxy, but others as well. That little spot is the Large Magellanic Cloud, satellite galaxy to the Milky Way. These spots, one of them is, I believe, a galaxy in the Virgo cluster, and 2 of them are distant quasars, which also emit in the microwaves. But they have a different spectrum from the black body. So if we correct for that black body spectrum and then use a different false color map to show the remaining fluctuations, we get this picture. Okay? So there are all these steps that you have to apply to the raw pictures in the microwave to correct them to see the fluctuations left, the imprint of the sound fluctuations produced by inflation. Now, I said that there are several relics of the Big Bang that we're going to study, and in particular, my talk has the title with galaxy formation in it. So I wanted to say something about galaxies as observed. Our understanding of the formation of galaxies and their structures in the early universe has really changed dramatically also in the last 10 years, thanks largely to the Hubble Space Telescope and also to new generations of ground-based telescopes. At the time this picture was made, so-called Hubble Deep Field, this was the deepest image of the sky ever taken. the Hubble Space Telescope pointed at a little tiny patch of the sky, very, very narrow area in the sky, for almost 2 weeks at the end of 1995. And that was a really expensive investment of time because there are lots of people who want to use the Hubble telescope, and the director said, this is so important that I reserve this time to use for a special project. The astronomical community was thrilled with the results because if the director hadn't pooled together the time available for those 2 weeks, nobody could have made such a map of the galaxies in the sky. And what we see is that at the faintest limits of our human view, everywhere there are galaxies. Just every degree of the sky, every square degree is just littered with thousands, millions, in fact, of galaxies per square degree. On this entire picture, I believe there are 3 stars from our own Milky Way galaxy, and everything else is an external galaxy. Some of them are large, relatively large, and you can even see spiral arms, spiral structure. Those are nearby galaxies. Some of them are so faint that you can't see these little speckles very well from where you sit. But astronomers have analyzed that image and taken more measurements and learned something about the formation of galaxies. I'm going to show another animation. See if I can get this one up, showing you the Hubble Deep Field right above the Big Dipper. And this is a nice little animation that just shows zooming into this small portion of the sky, first to show what can be seen with ground-based telescopes in that ground-based picture, magnifying it further to the limits of ground-based telescopes, and then filling in this amazing vista of what the Hubble Space Telescope saw. It's really beautiful. Astronomers couldn't get enough of looking at this picture and analyzing it. So now comes the question, how did these galaxies form? We've seen a snapshot of the universe less than 500,000 years after the Big Bang. We see galaxies 1 billion years after the Big Bang. What's the connection? How did the fluctuations we see go to form the galaxies? Well, there's several steps. First, we've talked about and seen now the seed fluctuations from the early universe produced, I see here I say 10 to the minus 35, there I say 10 to the minus 37. We don't really know when inflation occurred because we don't know the physics of these ultra-high energies. There's speculation, and we hope that by learning more about the fluctuations, especially one day by measuring the gravity waves from the Big Bang, we can say when inflation took place. Gravity waves will be a very good probe of the energy scale of inflation. I mentioned already the 2 outcomes of inflation. It makes the universe large and flat, and then leaves these quantum fluctuations, which become amplified through gravitational amplification. Gravitational amplification is nothing more than the fact that gravity wants to make things fall. I can't stand a pencil on its tip for very long because it is unstable. Gravity wants it to fall. If I start out with a little patch of the universe that has more than the average amount of matter in it, gravity wants to draw that together, make it collapse. Locally, it behaves like a little closed universe where the matter will fall back upon itself. Somewhere else, of course, there's a compensating lower density region of the universe, and that behaves like a little portion of an open universe, expands more rapidly. You'll see this when I show you an animation of how gravity amplifies these fluctuations. Now, there is one ingredient that you might think is unnecessary to this story, that is dark matter. Gravity works on us. We're not made of dark matter. Why do we need dark matter? Well, it's not so much a question of need as fact. Galaxies are surrounded by clouds of dark matter. Its existence has been inferred for about 50 years in clusters of galaxies. The evidence by now is so strong that it is almost universally accepted in the astronomy and physics communities that most of the mass in the universe is in this unknown dark form. But it is crucial for galaxy formation for the following reason. Before at times before the microwave background was released to us, photons and electrons scattered rapidly. That's why we don't see any earlier than 380,000 years after the Big Bang. We see only back in time to where hydrogen became neutral atomic matter. Earlier times and higher temperatures, we had ionized hydrogen, which is protons and electrons. And those scatter the radiation so much, it's like if you took an electron and you try to move it, it'd be like moving through molasses. You just couldn't do it. It's too much resistance to motion of charged particles when you have an ionized gas. That means that atomic matter is unable to experience this gravitational instability. Imagine you stuck a pencil on its end in a jar of honey. Well, it wouldn't fall very fast, would it? The viscosity would prevent the pencil from falling. And so the atomic matter is likewise held in this viscous grip of the radiation and prevented from doing much of anything until 380,000 years after the Big Bang, more or less. Dark matter, however, has no such interactions with photons because we haven't seen it. It doesn't scatter radiation. The universe would not be, the matter would not be dark and transparent if it scattered radiation. So the dark matter is free to begin clustering under gravity at much earlier times. And for about 20 years, we've recognized that it's a crucial ingredient of a successful theory of galaxy formation. I probably don't need to review for this class, but I'll do it anyway. I know that one group is going to be talking about dark matter and dark energy in its presentations next week. Dark matter is the invisible stuff that gravity draws into galaxies. Its distribution in space is clumpy. It has positive mass and negligible pressure, so it's a source of attractive gravity. It's detected so far only by its gravitational effects on galaxies or on light rays that pass by galaxies through gravitational lensing, or on the gas in clusters of galaxies. And we have a good idea of what it could be. There are two elementary particles that physicists would like to think exist quite independently of the cosmological needs. They're particles called the axion and the neutralino. In fact, I would be surprised if there is only one type of dark matter. I would be surprised if there's only one type of dark matter because the physics needs for these two particles to exist in particle physics models is strong, indeed compelling. One experiment may not be enough to find the dark matter, all of it. Dark energy is also invisible, but gravity does not draw it into galaxies. It is not the dark matter around galaxies. It is smoothly distributed through space, as best we can tell, and it's a source of repulsive gravity instead of attractive gravity. It's detected by its gravitational effect, not on galaxies, but on the overall expansion rate of the universe. And we have some ideas about what it could be, but they're pure speculations. Vacuum energy, cosmological constant, quintessence. These are all names for possibilities that are not compelling by any means. So I would be surprised if there is any dark energy at all. But, well, most people are surprised. So in a pie diagram format, here's the composition of the universe. As a fraction of all the energy in the universe today, dark energy 73%. Dark matter in the form called cold, 23%, and atoms 4%. And does that add up to 100%? I think so. That's the composition today. If you look at the composition 13 billion years ago, almost all of it would have been dark matter, relatively less would have been dark energy. The universe has just become dominated by dark energy within the last few billion years. Now, let's look at the fluctuations again and ask how they go from the early universe into forming galaxies. So I show here a small portion of the fluctuation pattern like that we might see in the microwave background. This is the type of pattern produced 10 to the minus 35 seconds after the Big Bang or so. Oh, one important thing about inflation. A key to its success is that inflation takes microscopic regions that are far smaller than a proton and magnifies them so that today they're bigger than our observable universe. So these fluctuations on all these scales, this might be megaparsecs or millions of megaparsecs or light years across in today's universe. Back at those extraordinarily early times, all of this was condensed into a size smaller than a proton, much smaller than a proton. And so subatomic processes could lead to the fluctuations that now range over cosmological scales. That sounds amazing, but it really is the prediction of inflation. Now let's take this pattern laid down a fraction of a second after the Big Bang and look at this pattern. I'm going to show you what the same pattern looks like 380,000 years after the Big Bang, at the moment we call microwave background decoupling. This is actually not a picture of the microwave background radiation I'm showing you now. Something changed. I'm going to flip back and forth between those two. What has changed? And what has stayed the same? What's different about those two pictures? Resolution. Now, it's not because I had a poor quality image program and I couldn't make good high, oops, don't want to go to that one yet. I couldn't make good high resolution images. I said that the fluctuations in the plasma of the universe were sound waves. Sound waves move outwards in space. In fact, I want to find a little animation here for you of how those sound waves. See if I can find this animation. That's not the right one. I'm going to bring up another window here because there's a cool little animation here. Ripples. So you want to make this full screen. Oh, this is Internet Explorer. Okay, we'll make do with Internet Explorer here. Somehow that got associated with this. So I'm going to replay this animation, but this is showing how fluctuations produced by inflation end up being spots in the microwave background radiation. And let's replay this here. So imagine you have a pond, and you drop a stone into the pond, and it sets some waves into motion. I'm not sure what that pond is supposed to be. Okay. Now drop lots of stones. Each of them makes a little pattern that spreads out. And then this has been false color coded, and it's shown you how this can be a small piece of the microwave background sky. All of this stuff is the fluff. What was important was that early stage where you saw the ripples spreading out from the first fluctuations. This happens with inflationary fluctuations. They spread outwards like waves in a pond. Not water waves, but sound waves. When those waves spread out, they smooth out small scale ripples into larger scale ones. And what you're seeing in this picture is exactly the smoothing out of the inflationary fluctuations as a result of sound waves traveling through the universe. By the time 380,000 years after the Big Bang, those sound waves had traveled a distance which was, about 380,000 light years, give or take a factor of a few. But that same order of magnitude. And the pattern you're seeing here is just a million light years across or so. So the sound waves have done that. They have smoothed out the fluctuations. And these are fluctuations, it turns out, in the gravitational potential. Now I'm going to show you the fluctuations in density. And density is not quite the same thing as gravitational potential, so it looks a lot more choppy. These were the seed density fluctuations that produced galaxies in a computer model. And I'll close this sequence by showing you the computer model positions of the dark matter 13 billion years after the Big Bang. There they are. And I'm going to go back and forth between these two. And I think you can see the correspondence. This is false color representation of dark matter. The place where the dark matter is dense are the brighter colors, red and yellow and white. The place where it's low density are black and blue. And what happened is that the places that were dense to begin with, a few 100,000 years after the Big Bang, as I said, those places, gravitational instability could take over and amplify the fluctuations. So over there, for example, over here, see those places where we had white before, we get strings, chains of galaxies, or of, at least of dark matter. This was only from a dark matter simulation. So in outline here, the inflationary fluctuations begin growing soon after the Big Bang. Cold dark matter fluctuations amplified by gravity. How do we get then to galaxies? Galaxies, the galaxies we see are made of stars and gas and dust, which are atomic matter, not dark matter. So what about the atomic matter? Well, as I mentioned, that's suppressed by the scattering of electrons and photons and protons and electrons until the end of the plasma era, 380,000 years or so after the Big Bang. And let us see what, I'm not sure now what animations I put up here. Let me see. Take a look at this one. Let me magnify this a little bit. Oops, wrong one. We're zooming in on a section of the cosmic microwave background. By the way, I got these beautiful animations from the WMAP website, most of them. And here we're seeing the formation of structure in the universe by a NASA simulation. And I'll play this one again because it's very pretty. This one is not real, though. You see how that galaxies kind of look painted on, and they... But what it is trying to show is how the WMAP satellite here, spinning around and measuring the sky, looks back through the galaxies to their origins in these fluctuations. Let's look at that again. Imagine going back in time to when these fluctuations were present. They start as very small ripples in the density of dark matter and gas, but gravity then amplifies them, and after a while, stars form. Whole universe lights up like fireworks as the first stars form. Stars and black holes. Some of those brightest spots must have been quasars turning on in this artist's rendition. So we see, when we look out in galaxies, the atomic matter. In the microwave background, we see the fluctuations that mainly acted on the dark matter. And we have a challenge to understand how galaxies and dark matter are linked together. Wrong one. I didn't want that window. There we go. So let's see what the second animation is. Oh, that one won't show. Well, here's the full picture. Take a little patch of the universe and just sit there and watch gravity amplifying the fluctuations in dark matter left over from the Big Bang. And what you might see perhaps would look like this. This is a computer simulation of dark matter clumping under gravity. So the white means that the dark matter is very dense, and it looks a bit like a swarm of bees all swarming angrily, and the swarms cluster together. That's gravity drawing in the dark matter. The only force in that animation is gravity. Let's look at that once more. It starts out all white. The universe was dense. See this tremendous expansion at the beginning? That's the expansion of the universe. The universe is out to here by now. And it's continuing. I suppose the universe is bigger than the room by now. I'm just focusing on this little portion to watch the formation of what might become a group of galaxies in the real universe through a process very much like this. So all these little condensations are places where the dark matter has been drawn together by gravity, and they started out as quantum fluctuations in the early universe, according to our models and as best we can tell from the universe itself. Here's another animation. This shows side by side the dark matter and atomic matter, hydrogen gas, in a simulation of a galaxy forming. This lovely simulation was produced by Matthias Steinmetz, a researcher in Germany. The dark matter swirls around like a swarm of bees, And if you look closely at the gas, you'll see a swirling disk, even with spiral arms. It's a really lovely simulation. Our theoretical model supposed that the dark matter first condenses. It has most of the mass and most of the gravitational effects. The atomic matter, gas, what we call baryons, falls in and moves a little differently because dark matter particles can pass right through each other. They don't have any collisional effects, whereas gas cannot pass through itself. Gas will flatten into a disk, rotate, and shock, forming, for example, a spiral pattern or forming stars. That simulation is so pretty, let's look at it again. See, dark matter is already collapsing. And now we're going to zoom in on the cloud of dark matter and the gas within it. And look, there's a little satellite galaxy there that's whirling around and it's going to get stripped apart. That happened to our own galaxy. It ate some of its neighbors to get to its present state. And it's in the process of eating some of its neighbors. The Large Magellanic Cloud doesn't have too many billions of years to live before it gets swallowed by our galaxy, just like that little denizen did. So what have we learned from the last 10 years of studies of galaxy dynamics and of the universe? Well, starting from inflation in the early universe, galaxies can form, we believe, and cluster as observed, but there are some requirements. Most of the matter must be dark matter, not atomic matter. And the total matter, dark plus atomic, can only make up about 30% of the critical density. This was known long before the WMAP satellite results were announced earlier this year. This really has been the paradigm for about 10 years. The dark matter must be cold. I haven't talked much about that, but it turns out that just as atomic matter has a temperature, dark matter can have a temperature. And if the temperature is too hot, that suppresses the effects of gravity being able to collect the particles and to form dense clumps. And the technical requirements that the particles must have been non-relativistic at these times, matter era, and that excludes, therefore, neutrinos. There are more particles in the universe than protons, electrons, and neutrons. There are lots of photons. In fact, there are about 6 billion photons for every proton or neutron in the universe. We know that from the microwave background radiation. And there are a comparable number of neutrinos to photons, almost the same. Neutrinos recently have been measured or inferred to have a non-zero mass. So neutrinos make up some of the mass of the universe. But they make up a very small fraction, far less than the atomic matter, we think, or at least less, somewhat less than the atomic matter. We're not completely sure of the masses of the neutrinos, only of mass differences between different neutrino types. But we know from the physics of neutrinos that the dark matter cannot be the neutrinos. Dark matter has to be something else. And as I've mentioned, there are actually two quite compelling candidates from particle physics called the axion and the neutralino. Well, we haven't answered all the questions yet about structure formation in the universe. I suppose the top questions for study in the next decade or so will be, what is the dark matter? Will it be discovered in laboratory experiments this decade? I think it probably will. I'm hopeful. If not in small-scale experiments, then perhaps at the Large Hadron Collider in CERN, which will turn on starting around 2007 or so, and search for a new physics called supersymmetry. These could be supersymmetric particles. What is the dark energy? That's a big mystery. Not even what is it, but or why is it there? But why is its abundance so close to that of dark matter? Now, you'd say, well, it's 3 times the abundance of dark matter. That doesn't sound very close. But remember that the ratios of dark energy and dark matter change with redshift. They redshift differently. And so that means that the dark energy and the dark matter were about the same a few billion years ago. Now, if you think of all the length of time from Big Bang to trillions of years, why is it that the dark energy has become comparable to all the rest of the energy in the universe just about when the sun was born? I think we had a problem set asking was it before or after the sun formed, but pretty close. Why? Why do we live in such a special time that the dark energy has just become important now? I don't know. That is one of the big mysteries of physics. And it bothers me. It bothers a lot of people why this should be so. Can we understand the astrophysical details of galaxy formation? I showed you computer models, computer simulations. The physics that underlies especially the star formation in those simulations is hideously complicated and very difficult to simulate. So we don't actually know that much about the details of galaxy formation. There are outstanding questions about the sizes and shapes of galaxies and the dark matter clouds around them. There are lots of outstanding questions about how and when stars formed, and also black holes. Supermassive black holes in the centers of galaxies, and of course the lower mass black holes that we see accreting in our own galaxy. So that's the end of the presentation. Thank you very much for your attention. And if you have any questions, I'll be happy to take them. Ted.
The simulation with the dark matter and normal matter, do you get the same kind of rotational curve for the galaxy? You know, it's supposed to be flat as you go further out radially? Or is that using like constraint for?
Well, this computer simulation really doesn't have the resolution to say very much about the rotation curve. The gas is modeled using discrete particles. You can see the particles whirling around. And there are a few thousand particles of gas here, maybe 10,000, but I think not even so many. So the details are only crudely modeled. The simulation does show actually a problem, that what tends to happen in this cold dark matter model is that the gas condenses more than it should. The gas disks of galaxies are too small in these models compared with reality. Now, most people think that that's a problem with the simulations and not a problem with reality or a problem with the physics. But until we can use many more particles or different computer algorithms or somehow model the physics better, we won't be completely sure. So the galaxy rotation curves are still kind of one of those fully unresolved questions.
Start with the amplitude fluctuation from the W map, and then take those to actually create the galaxy. And you get this, I mean, roughly the size distribution and things like that.
Well, so the size of galaxies depends a whole lot on this atomic physics and star formation and related processes. That is really too hard to do completely right from first principles. So people have to use some approximate treatments of the gas dynamics. And that means that it's hard to predict the size distribution of galaxies because you have to, the physics is too hard to do a completely accurate calculation. So you have to build in the size distribution if you want to make sure your calculation is at least giving you plausible answers. And that's bad. That means that we don't have much predictive power with the simulations, at least not as much yet as we would like. So there's lots of work left to be done in this field.
I understood you to say that we might detect dark matter, but we won't detect dark energy. Is that because it's so diffuse? Or will we only have a theory about what it is?
Well, one should never say never, but I'll stick my neck out and say we will never observe directly the dark energy. I'll make a categorical statement. I just don't believe we ever will, because whatever it is, it's not anything like standard particles that would collide with anything in your detector. So I'm afraid that we'll only have theories for the dark energy. Maybe we'll learn enough from astronomy that we can narrow down those theories to a very small set, perhaps even a unique theory. But discover it in the laboratory, I don't think so. Ted.
But if the dark energy, I mean, has some gravitational attraction, I mean, can it be absorbed by black holes? Could it be
Well, that's a good question, and I have to be careful since it's a technical question, and I don't want to speak wrongly. It can't be captured by black holes in the way that normal matter can, because remember, the dark energy doesn't clump. It's smooth. What's more, if the dark energy is a cosmological constant, you cannot even clump it, even by the gravity of a black hole. It's still smooth, even in the presence of a black hole. So no, if it's a cosmological constant, it cannot be captured by a black hole. If it's not a cosmological constant, but some form of dark energy or quintessence field, perhaps it can be captured by a black hole. I don't know enough. That would depend on the model, and I can't tell you the details.
What are two theories relating to the existence of dark energy sort of begin to emerge? Because it's something I just kind of started to hear about recently. This has been out for more than 10 years.
Well, the idea has been around since 1917.
Right, but okay.
And that's Einstein's cosmological constant. Now, Einstein introduced it as a term in his equations to stop the universe from expanding. And that was a pretty foolish thing in hindsight. It didn't have another interpretation until the 1960s, when the Russian cosmologist Zeldovich pointed out that what we call vacuum fluctuations in particle physics would behave exactly like Einstein's cosmological constant. Now, between 1929, when Hubble discovered the expansion of the universe, and about 1990, the cosmological constant was out of fashion. Einstein called it his biggest blunder. So who am I, cosmologists would say, to invoke it? There didn't seem to be any reason to consider the cosmological constant. Things started changing, though, in the 90s, when the evidence accumulated that the dark matter and atomic matter did not have enough density to close the universe, and yet there was theoretical support from inflation that the total density should equal the critical density. So some bold physicists in the middle 1990s proposed, resurrected, if you like, the dark energy, the cosmological constant. Even so, it wasn't taken very seriously until 1998, when the two groups of astronomers looking at distant supernovae published their astonishing discovery that the universe is accelerating. And since that time, it's been difficult to argue with the conclusion that dark energy makes up most of the mass of the universe. So we don't know what it is, and we haven't known about it for really seriously for very long at all. Ted?
The dark matter, you detect experimentally, it only interacts gravitationally. How are they going to detect it?
So it is possible that these particle ideas for dark matter are wrong, and the dark matter could be something that has no interactions except for gravity. Theorists are very clever, and they make models, parallel universes, shadow matter. There are various names for matter that would interact only by gravity with matter in our universe. But I personally feel that those are contrived. There is no reason to invoke parallel universes or shadow matter to account for the dark matter. There are very good arguments for particles called axions, which can solve problems in quantum chromodynamics, the theory of how quarks interact, and for supersymmetry and supersymmetric particles. So in fact, I would say that it is likely, many physicists would agree, it is likely that at least one, perhaps both of those particles will be discovered in the next decade due to their interactions with ordinary matter. Perhaps in 10 years, I'll be proven to be wrong, and then I will be happy. I'll be even happier if I'm proven to be right.
If you assume that and then go back into the dark matter simulation and try to, you just made the assumption that there is some interaction, and then go back into this simulation,
Oh, those interactions are so weak that they would have virtually no effect whatsoever on the simulations. There was a, the Boston Globe has a science section on Tuesdays, and there's a science writer named Chet Ramo who writes a column. Last Tuesday, a week ago, he wrote a column about dark matter. You might want to go back to your Boston Globe and see it. He kind of poked fun at the cosmologists who think that dark matter exists, but they really have not much evidence to back it up. Actually, I would disagree with Ramo. I think that there's a lot of evidence for dark matter. I don't mind being poked fun at, though.
He also said dark matter was 90% of the universe, so I sent him an email complaining about that.
What was his response?
Well, he asked me more questions, and I told him to go to the WMAP site, and I haven't heard from him since.
He's a fine writer, but if you write for the newspaper, get your facts right.
Oh, he is very good.
Okay, well, thanks, everyone.
I want us to appreciate Mike Leoncini, who's never made a mistake during any of these things and always gotten everything to work. So
thank you, Mike. And it's going to be time for the rest of you to